So we have determined the one of the exact solutions of Navier-Stokes equation for a specific flow under several assumptions that we described when we were describing the problem that is to be considered and what is called as Couette flow, and the flow that takes place between two infinite plates. We make a few observations and remarks about the same solution. It's good to verify the results that we determine by solving a problem, that is, analytically solving a problem, and it's good to see if the same results can be obtained through experiments or other means to verify them. We also note that the only contribution that is coming from the stress tensor, which we write it in component forms, then is coming in these two terms, this one as well as this one. All other terms are zero and we don't get anything from this. Now dimensions are the same as that of the force per unit area by definition, and that is the force that is acting on the bottom face of the fluid element. Therefore, tau of yx equals mu into v over h, and it acts in the negative ix direction. The shear force per unit area on the wall is equal and opposite to this. So this is the only force that is acting, and that is because of the viscosity. When the plate is moving, no external pressure is being applied. The only force that is generated or in the motion that takes place is because of this viscous action. And you remember that when the upper plate tries to move in the x direction, the fluid at the bottom will try to resist that motion. So that will be the forces there will be in the opposite direction as compared to the one that is in the upper direction, and where the velocity or the upper plate will try to carry the fluid in the positive x direction. So these are the normal thing, and the shear force per unit area will be mu v over h, the unit vector I, and unit vector I is obviously denoted in the x direction. So these are the forces, the stress, the pressure that is being applied on the motion of the fluid that takes place between the two plates as defined, where the plate at the lower end at y equal to 0 is fixed, and the plate at this point is moving with the certain velocity given by capital V. The z component of the linear momentum equation is uncoupled from the rest of the equation, so in a way that is not related to it, and that explains why we got a hydrostatic pressure distribution in the z direction. And also the forces, that is the components that are coming, are only two components that have some non-zero value. As far as application of such an ideal type of problem is that this kind of situation that takes place in the measurement of viscosity and what we call as viscometer. And the only thing is that instead of the fact that the plates are moving in rectilinear direction or in the x direction, the other plate is fixed. This one, viscometer, is normally its geometry is such that it's given a rotation. So in this case, the fluid motion is taking place between two plates such that one plate is fixed while the other plate is being given rotation. So you can see that this kind of yellow color, that is where the fluid is taking place. And if the radius of the inner plate is Ri and the radius of the outer plate is Ro, the Ro is given a motion angular velocity such that it moves with an angular velocity omega. If we try to magnify it, then we see the stress forces, how they generate the motion, and they will turn out to be this, very similar to what we have in the rectilinear directions. So these will be the forces, and from this, in fact, we shall be obtaining the value of mu, the viscosity, and this setup is used for measurement of a fluid. And you can see that mu, the unknown thing, is on the left hand side, while the right hand quantities on the right hand side are measurable. So that kind of concludes the discussion of fluid flow between two infinite plates, such that one plate is fixed and the other plate is moving with velocity capital V. And other conditions are indeed there, that the flow is steady, that is time independent, it's incompressible, no change with respect to density, etc.